These are the upscaled and colorized lessons of Alexander Lippisch. Lippisch was a pioneering German aeronautical engineer renowned for his significant contributions to aerodynamics, particularly his work on tailless aircraft and delta wing designs. His career spanned crucial decades of aviation development, marked by a persistent exploration of unconventional flight concepts.
Well, if we want to talk about drag, aerodynamic drag today, we must be aware that this is one of the most intricate problems in fluid motion. Many years of theory and scientific work was spent on this question, but we have still today basic problems which are not well explained. Now, if you think about the drag of a body which moves through the air, you would say, all right, the drag is caused by the friction of the air against the body. All right, but what is friction? Well, if you look it over, friction is the resistance between two bodies moving against each other. Here the air against the body. All right. Then the resistance is a drag. So there you are again. And what we have to do is we have to explain friction, aerodynamic friction. Let's see how we could do it. Well, we think, for instance, of, let's say we throw a stone. And think of this motion. Now, you might realize that if the stone goes through the air, there might be some air particles which are still attached to the stone. So the stone makes, while it goes through the air, a certain motion in the air. It propels a column of air which is behind the stone and runs then with the stone. So, well, if I can explain it to you on a blackboard, would be probably this. Here is a stone, and the thing is moving in this direction. Then we have a certain amount of air which is still attached to the stone due to the fact that little particles stick on the surface. And when the stone is there, then there is a column of air behind the stone which is filled with air which is moving also in this direction. The stone is moving in this direction, so the air is at rest. You can actually feel this if you, for instance, stand there where a train goes by or a car, and you can see it in the dust cloud which is behind such a car if it goes over some of our old travel roads. But you can see it even better if we look at the smoke tunnel. Now, I don't have a stone in the smoke tunnel. I have a nice, round, circular cylinder. But it is a good presentation and a good example to look at this. Here it is. Now, well, we see this piece of air which is more or less attached to the body. But we see one other thing, very peculiar. This is an oscillation in the wake of the body. You know, we call this part, this air, which is moving with the body, we call this the wake. Or, let's write it here, the wake of the body, the wake in the flow of air. And in this wake, we have here apparently a very distinct oscillating motion. Now, we might not see it clear with this normal speed, but we can see it much better if we take of this flow picture a high-speed movie and then look at the high speed. And there it is. Now look at this. Isn't that fascinating? This regular motion of a generation of large vortices which are now coming off periodically, one at a time from the upper or from the lower corner of this round body. Such a phenomenon was first investigated by Professor von Karman, and therefore we call this wake, which we call also a vortex street, the Karman street. Now, the generation of these vortices certainly needs lots of energy, and therefore the drag is not only here friction drag, it's actually only a very small part of the drag, but the main part of this drag is caused by the generation of the vortices, because there is energy needed to make such vortices. And this energy must correspond to the drag times the velocity of this motion of the body through the air. Now, if you want to stop this, what could you do? Well, you could do one thing. You could probably make a plate back there on the body, which then separates both parts of the flow, and in this way damps out this oscillation. Well, let's try this in this tunnel. Now we have here that cylinder with a plate in it, which we call a baffle plate, so that we would stop the oscillating motion of these vortices. You can see it here very well. You see now this part is mainly uniform and there is no oscillation, but still at the wake far behind the oscillation begins. It actually is something which has some similarity to the scattering of a flag. And if you wanted to reduce now this large wake, which is still in here, and which gives us a dead air zone, which again would cause drag, we have to fill it out and make this part of the body. That means you have to do something here, so that you would come finally to a round piece which has a fairing behind. And if you smooth this out a little bit, then you get a shape which is approximately like this, and which we call a streamline shape. You will see this as our next test in the tunnel. And let's just put it in there. Takes just a few minutes to mount this streamline section, which you see here. You see, this is now derived from originally a round rod, which is then a little bit elliptical flared out here, but mainly has a long and smoothly decreasing tail end. This is much more important than this, because we have seen on the round rod that the flow here on the front part was all right. We had only trouble at the rear. So if we make a blunt nose, this wouldn't bother us. But we have to fared out nicely and make a quite long tailpiece on it so that the air can follow such a surface smoothly, like this. Now, let's look at this in the tunnel. Start the blower and the lights, and there we are. You see, now I might adjust this a little bit. You see that we have now stopped the vortex motion almost completely. And we have only a wake which contains now here air which moves with a lower velocity than the outer one, because due to the friction on this surface, the air which is narrow to the surface was slowed down and has lost a certain part of its momentum. On the other hand, we see that a streamline which is near to the body now suddenly begins to jiggle and to blur out. We call this the transition from a smooth laminar flow to a turbulent flow condition, which we may see even much better if we look now to pictures which we have made in our three-dimensional tunnel. Now, before we see these pictures on the three-dimensional tunnel, I probably have to explain to you a little bit how this tunnel works. You see, the tunnel which we have here is a two-dimensional tunnel. We call it this way because we have just a narrow strip of smoke or flow which is closed in by two narrow glass walls. Now, a three-dimensional tunnel is a large cross-section which is actually somewhat rectangular, and then we mount the model from one side of the wall, and here we have the flow through it. So this is kind of a box enclosed where the flow goes through. And the models itself, which you will see in these pictures, are, for instance, this straight wing. You see just a half of a straight rectangular aircraft wing, which is now painted black so that we can see the smoke lines very well, and we release the smoke on this leading edge. You see, we have very fine holes all along here and part of the holes along this tip, and we blow now the smoke into the model through this tube, where we also mount the model so that we can change its angle of attack. Another model which you will see is this swept wing model, which is mainly the same kind of construction, you see, with the fine holes on the leading edge. The smoke is introduced from the side into the hollow interior of this model. Now let's look at one of these pictures. We first see the straight wing mounted in the tunnel, and we see it with normal speed. When you see it with normal speed, you don't see much, but when you look at this picture now, where we have a high-speed movie or slow motion picture with about 1500 frames per second, then we see suddenly the transition between the smooth flow at the beginning of the surface and the turbulent flow, which is then at the rear. At the swept wing, we have in some way a different condition, because due to the swept back, the flow is not uniform all over the surface, but at different stations of the wing, we have different conditions, which we see very well in one of the next pictures. This is this one. And there you see this wing from above. And you see that the transition at the outer part begins much earlier than at the inner part of the wing. Now here you see it from the side view. And I think you should observe this picture very well, which shows us so clearly that we have first waves on the surface, and then these waves overroll and finally break up like the breakers on a surf flow. And then the turbulent motion over the surface of the wing begins. Actually, this is not stalling. It still sticks to the surface, but with this turbulent motion. Now, to see this even better and to explain it more clearly, we have put a large straight wing in the 3D tunnel, and you see here a picture of this large tunnel, large wing mounted in the tunnel. You see it here from the side view, and it is just a picture to see how it is arranged. When we now look more close on this model, then we see again this wave motion, which is very distinct and actually is one of the most intricate problems of surface flow. Why is it so? Why are waves formed? And why are then these waves suddenly broken up into a turbulent motion? When we want to see this more clear, we can now look at one smoke ribbon. So before we see this picture of the smoke ribbon on the surface of the wing, I will explain it a little bit to you, because it's in some way difficult to see. On another way, this picture is a very important one and actually is the first visual observation of such a process. You see, we have the surface of the wing here, and we have a small smoke ribbon which just floats above the surface. Now, while it floats over, part of it is decelerated, it's slowed down due to the friction, so this stays back, and finally the outer part rolls over and forms here first waves. It rolls over, forms waves, and then rolls over completely from the vortex, which now disattaches and goes to here. And instead of now continuing as a vortex due to conditions of instability, this thing explodes and forms a big bubble of turbulence, a turbulence bubble which goes over the surface. Now, when you see this picture, you must think that since this is white smoke and we have a black surface which is very smooth, you see also the mirage, the reflection of this white smoke on the surface. So actually you see the smoke itself and its reflection. So don't bother. Now there's a picture. Only the upper part is the smoke and the lower part is the reflection on the black surface of the body. Here you see it very clear. This picture was taken with 3,500 frames per second. And we are actually very proud that we achieved this picture. I'm very thankful to the photographic department of the Collins Radio Company who helped us with this, and to my assistant, Mr. Schroeder, who made all the arrangements for this test. Now, if you see all this, and you see these friction on the surface, on this breakup of the boundary layer, then you think what could you probably do to improve it and to prevent first a large turbulence, on the other hand to reduce the total drag due to friction on such a surface? Well, first of all, you could do this. Since the lower layer on the surface is retarded and is practically dead air, you could suck it away. That means you could take a surface and have a little slot in it, and when then this layer, which is retarded here, comes to this point, you suck it away, and a flow which has more momentum comes back on the surface. In this way, you would reduce the tendency of the surface flow to break up. Another method would be to do the reverse thing. That means you would make a slot here which would blow a certain amount of fresh air into this layer, and in this way propel it. Now we have here a model in the tunnel where we might show you how surface suction works. This model is a streamlined section, and we have slots in it, and through the slots we suck. Now watch it. When we turn the suction on, there it is. Then at once you see that the wake becomes much smaller, and you see also very distinctively the steps of this streamline where part of the dead air which is on the surface is sucked into the model. Now we have a blowing model in the wind tunnel, and I have made this extremely blunt. That means I have made a streamlined section which is really reduced to a very small size and very big, so that you might see how such action really works. When we, for instance, try now to turn on the blowers, then you will see that we can attach the flow, and we get a very nice and smooth flow over this surface. Even if I give angle of attack, then you see that the flow still holds on such a very narrow curvature of the body. You see, in this way you can reduce the drag considerably. The transition from this state with the large vortices and the suction we have also taken in a slow motion picture, which you see now here, and you might observe very clear the sudden reduction of this wake and then the close-in of the streamline. But when you think this vortex formation is mainly the major source of drag, and if we look at a wing, at a full wing with all its span in the tunnel, then you might observe another cause of vortices, which we will deal with in the next lecture, but I might show you just a few examples of this type of a flow. To show you this formation of vortices which make drag due to lift, we have here a model in the wind tunnel which represents a small wing. And you will see that if I increase the angle of attack and the lift of the wing, then you see suddenly a formation of large vortices from the wingtips. Look at this here. Why is it so? Well, it's due to the fact that we have underneath of the wing a higher pressure than above the wing. So on the wing tips, this pressure differential must equalize by flowing around the wing tip. And this flowing around the wing tip with the translation of the forward motion gives you a spiral motion which forms this vortex. Now if I give negative lift on this wing, that means if I turn it this way, then you see the vortex rolls the other way. But you can see this formation even better if we go to a model which shows us only the wingtip in the tunnel. Now you see this vortex formation on the tips of the wing cannot be done by nothing. You have to put new energy into the flow which makes the thing rolling. And this energy has to be provided by the propulsion system of the aircraft. This drag, which is caused by the wingtips, by this flow due to lift, is caused induced drag because it is induced by lift. Now we have this wingtip model here in the tunnel, and when we give angle of attack to the model, then you will see very clear how such a wingtip forms. I think it's quite exciting to see how nicely even such a flow line stays together while it turns violently around. You see, it is no friction there. It's just a rotational motion which is introduced here into the flow. Let's give it some more angle of attack. You see, this holds for quite a while together. But this is probably the normal position as it is formed on the wingtip. Now, in the next program, we will have many examples of this type of a flow phenomenon, not only on a straight wing, but on the modern swept back wing, on delta wings, and I will show you quite some exciting pictures on this matter. I hope you will not miss this program. On the other hand, we will have pictures from the 3D tunnel too. So, up to the next program, goodbye and auf Wiedersehen. In our last program, we talked about the aerodynamic drag, the air resistance. But the air resistance actually is not the only thing which you have to overcome with the power which you build into an aircraft. See, you also need power to make the lift. Two types of power you need. Power to overcome the air resistance, just to make it moving forward, and power to produce a lift. This is a difference between a land vehicle, like a car, or let's say a train, and an airplane. With a car or train, you need the power only to make the thing moving, to overcome the friction towards the ground and internal friction and things like this. And the weight is supported by the solid ground. But with an airplane, it's different, because when you fly through fluid matter, through air which can yield away. And in this way, you have to bring all the time new masses of air into play to be supported by a downward motion of these masses which continually come into the vicinity of your aircraft. You could probably compare this with a very simple example of a man who wants to cross a pond on some logs which are swimming in the pond. And let's assume that these logs are not large enough so that he could just stand on one of these logs. Now, if you think of this, we might sketch it just up. Then you have here, for instance, the beach on the one side, and then there are the logs in the water. somewhere around here. So, and on this other side is the other beach. Now this fellow wants to run over it. And while he runs over it, the logs give way. So actually the picture which you would make while he is running shows that the logs he just touched and is supported by them are underneath the water line. And the next one he just begins to jump on is beginning to sink, while another one he has just left comes slowly up. And here is this fellow now, which we might sketch in the simple way, standing up there or running up there from this to this. So actually the line of the logs, if you connect all the centers of the logs, is a curved line. And this fellow has to run all the time uphill because the logs gave way. So the log on which he is standing is lower than the ones where he wants to get at. And he has to get up all the time uphill. So even if this whole motion would have no friction, he would still have to do work because he has to work uphill. And this is the same with an aircraft, because also the air gives way, and therefore when you have an aircraft flying here, let's sketch it up, might be this would be some kind of an aircraft. So then the air which supports this aircraft is in a downward motion on the spot where the aircraft at the present time is. And this aircraft, instead of flying in air which comes direct against it, has to fly in air which comes above. So that even if you think of this being so smooth that there wouldn't be any friction, you still have to work because you have to fly actually against air uphill. And in this way, you have to do work. Now, this is a general concept of what would happen and why you have to do work to produce lift. But if you look at this process a little bit more specifically, that means look at the wing itself and at the motion, what would be around the wing, the motion of the air, well, then you must say, where does the air yield away? Now let's look at the aircraft, let's say from in front. Here's the fuselage. So now since this aircraft is supported by the air, you must have a pressure differential across the wings. So underneath of the wings, you have apparently positive pressure, as we have seen it in this tunnel, and we have demonstrated it. And above the thing, you have negative pressure. And this pressure differential supports you because pressure underneath, suction above, gives the lift. But what happens on the wing tips, on the corners, on the edges? Well, there a mass of high pressure air meets a mass of low pressure air. And since plus goes to minus, the higher pressure air wants to flow towards the region of lower pressure air. This floats around the tip, and this floats around the tip. And while you are now in forward motion and have this motion around the tip, the resulting motion of these air particles is what? A spiral. And if you look at this from in front, you are flying this way, let's say, then you would have here a motion of the air which comes around and goes backwards, and this backwards motion gives you what we call, well, what do we call it? A vortex. And these vortices are originated on the wing tips of the aircraft. And they produce this downward motion of the air we talked about before. But even if we probably go a little bit more deeper in this problem, we like to see it at least in the smoke tunnel. And I have here a model of a wing. You see, this is a plain straight wing. These are the two tips. And I put it in this way. And I have here a gadget so that I can change the angle of attack with these controls. Now let's put this thing in there. You will then observe one thing. Well, as long as we have no lift, we wouldn't have any pressure differential, because then pressure on both sides of the wing is the same. So result is that we wouldn't have any of these curls on the side, these wingtip vortices. If we have more lift, we get vortices. The moment we increase lift, the vortices must get stronger and stronger. And this we might see here pretty good. Now let's adjust this model. You see I have here two handles. The one is used to put the thing straight, and the other one is used to give an angle of attack. An angle of attack is this one here. Now let's put it, if we have now smoke, then we can probably see it. There it begins. Now let's put it first at an angle of attack where we have no vortex or no lift. That's this position, for instance. You see, the wake behind this wing is mainly due to the friction on the wing surface. We get then resistance. Now we change the angle of attack to a larger angle. That means we make lift, and there are the vortices. You see them very nicely. And even to see it better, we have another model, only the model of a wing tip. That means an enlarged piece of, let's say, this wing tip. And we can put it down into the tunnel now in this way, and can see the formation of the vortex even more definitely. This model we put now in the tunnel, this wingtip, is actually only half as wide as the tunnel itself is. In this way, we see kind of a three-dimensional development of the vortex in this small tunnel. Now I think the thing is in there, and we have adjusted it so that we have no lift. You see, then we have a little negative angle of attack. Now if I increase the lift, excuse me, it takes a little time there. Then you see at once how this vortex develops. You see very clear these curls, these spirals, beginning here while the flow goes from the lower surface to the upper surface. Here underneath we have pressure. Above we have suction. And the air flows from the pressure side to the suction side. Now it is carried away, and due to this rotation and translation, we get this vortex. It's interesting to see that this is not a motion which causes friction, because these lines stay very well together. That means it's a completely frictionless flow around the thing. But due to the production, to the generation of the vortex, you need a certain amount of energy. You see, you cannot produce just a vortex for nothing. You put this rotation into the air, and the amount of rotation takes away a certain amount of energy, which you have to counteract with the power in your aircraft. Now, when we put this in negative angle position, you see, go through the zero lift and go to the other side, then you see that the vortex starts the other way, because now we have pressure above and suction below. You might think that what we see here in this pretty small, more or less two-dimensional tunnel is only a kind of a visualization, but it might not be completely true. But we have therefore made some pictures in our three-dimensional tunnel. That means a tunnel which is so wide that you can put at least half a wing in it. I think you remember I told you once that this tunnel has a rectangular cross-section, and we fasten the wing on one side, so we see half of a wing, and the vortex develops then on this wing tip. And we have made several pictures where you can see them. Here are now the films. First, a picture where we see where the smoke comes out, and we begin with no speed at all. Excuse me. The moment we blow, the moment you see that the flow which came out underneath starts around the wing tip and flows to the top and forms behind this wing a vortex. Here we have, for instance, a condition where we have no lift. Now we increase the angle of attack, and at once the rotational motion around the tip starts, and you see very distinct these particular flow lines which now spool up all into kind of a rope which forms this vortex which starts from the upper part of the wing tip. We have then a picture where you can see this from above, so that you can observe that the core of the wingtip doesn't start just at the corner of the wing, but more or less at this edge where the upper surface of the wing ends, and it is a little bit set inside, so that the distance between the cores of these two wingtips is not the true span, but it is a little smaller than the span. This causes a certain loss of energy, because then the vortices are even stronger. With particular changes and particular forms of the wingtips, you try to improve this. Here we have the picture from above. But we see it even better if we can look at a film which is taken in the same tunnel just from behind, so that we observe the rotation more clearly, and then we can do it here. There it is. And we have released also some smoke from the leading edge to show you that not only the air masses which are just around the tip produce this rotational motion, but that also other masses of the air which are in between the two vortices take part in this rotation. The core of the tip vortex is in some pictures to see as a fine dark line. Actually, these vortices are very stable and stay there for a long time. So if some airplane has flown over a certain region and it has left this place, the tip vortices which he has produced will still stay there. Here is a very nice picture direct along the core of the vortex, where you see very well this rotational motion. Again, a picture from the side view where we see the single flow line, and we observe one thing, that the slope of the line increases towards the rear because this rotation is caused by the lift. Now, the front part has not all the lift, but until you get to the rear end, you have assembled all the pressure differential which is there, and therefore the spiral gets steeper and steeper towards the rear. Now, we might think how this vortex motion ties in with what we talked before, that the air is moving downward even at the point where the aircraft flies. You see, when we have here the wing and these vortices on both sides, they induce a downward motion behind the wing. But when you see it from the side and you have here this vortex and here this vortex, this motion, this downward motion is even beginning before the wing is at this point, so that when you look at it from the side view, there is a downward motion of the air at the point where the wing is. And in this way, we have to go uphill, actually, all the time. And the work which we need to produce lift is the work which is necessary to go in this uphill direction. Now you think, what could you do to reduce this? Well, let's think about it. We have, as we said, underneath the wing, the higher pressure, above the wing, the lower pressure. If we would distribute the load on the wing over a larger distance, a larger span, we call this distance from one tip to the other tip the span of the wing, then certainly the pressure differential across a certain section will be smaller. And therefore, when this pressure differential from below to above is smaller, then also this rotation is smaller, and we get smaller tip vortices. And that is the reason why, for a highly economical aircraft, we should have wings which extend into large span. And since we cannot increase the surface of the wing, otherwise we would get too much surface friction, we have to have a very slender wing with a small chord, the chord length we call from the leading edge to the trailing edge, and a large span. And this ratio between the span and the mean chord of the wing, we call it the aspect ratio of the wing. You might hear it very often when people talk about it, aspect ratio. And you see that aircraft for high flight economy have high aspect ratio. All these laws of the vortex motion and the vortex formation on the wings were discovered originally by Lanchester, and the theory about this whole problem was mainly worked out by Prandtl in Göttingen. It was first applied on gliders, and I have here a picture of a high-performance glider we did a long time ago, where you see very well that we have a very small chord and a large span. Actually, this aspect ratio of this particular high-performance glider was 20:1. That means the chord, the mean chord of this wing, is 1/20th of the span. And if you look at a modern transport aircraft, at an airliner, you will see that such an airliner has, again, a very slender, long wing and uses the main basic principle of high flight economy in generating lift as we did it once on the high-performance gliders. Now, you could do that not all the time. You couldn't build a very slender wing because, well, you must think that when you fly, you have to suspend the weight. And when you build a very slender wing, then you have to have a very heavy structure within the wing to keep it from bending too much. And therefore, there is a certain technical limit in having wings with high aspect ratio. And you sometimes think of methods to make this process more efficient with normal sized wings, especially if you come into the high-speed flight condition where you cannot afford to make long, slender wings at all due to other laws which are connected with the high-speed and supersonic flight. And there you see, for instance, an application which you can observe very often on jet aircraft, on high-speed aircraft, where you see that on a wing which has a normal span, we placed out there two streamline bodies which now are used as tanks, so-called wingtip tanks, or for housing radar equipment, anything like this. This has a meaning that when you put such a rounding on the tip, then this motion around the tip will be more smooth. And you actually can, in this way, improve the flight efficiency of such aircraft. We have made a picture of such a wingtip tank on a normal wing in our tunnel, and you will see it here. Now, what we learned today is this. The formation of the wingtip vortices causes a downdraft on the wing itself, and in this way needs power to climb all the time against an air mass which is in the downward motion. This downward motion is induced direct by the aircraft itself. And therefore, we need power to generate the lift. Actually, it is so that in cruising flight, 50% of the power is needed to overcome the air resistance, the friction drag, and some turbulence. And 50% of the power is needed to generate the lift. In our next program, we want to talk about the development of the aircraft type of the original biplane to the latest types of aircraft as we have it, for instance, with the swept wings. As you see here, a model of it, which we just put shortly in the tunnel so that you might observe also the flow around such a wing. Now my assistants have mounted this swept wing model in the tunnel. And if I turn the light on, we can see very well the flow around such a wing, where you also see the formation of the tip vortices. But let's talk about this in our next program, where we will explain the development of the aircraft configuration from the biplane up to the latest types, the delta wings for the supersonic flight. Up to this time, goodbye and auf Wiedersehen.